Hello everyone, I'm Caleb, and welcome to Wattage Wisdom, where we believe that anyone with the right motivation and internet access can become an expert in any field they desire. In this video, I'll be going over how you can build your own artificially intelligent neural network. So don't forget to like, subscribe, and reach out over email with any questions, topic suggestions, or collaboration requests. So in our last video, we covered what a neural network is and how it learns. Now we'll take a look at these steps required to build an effective neural network and run through the entire development process. Before we get into things, it may be beneficial for you to have access to Google Colab and have the proper deep learning library imported so that you can follow along and try these concepts out for yourself. To do this, you can simply go to colab.google and open a new notebook. All that's required is a free Google account, which you may already have through a Gmail. And this is going to give you access to computing processing power like GPUs, TPUs, which can empower you to develop and train neural networks through only your web browser. Once you've opened up Google Colab, the first thing you'll want to do is import TensorFlow as TF. This is done in the example code I've included here and is essential as it'll give you access to the powerful TensorFlow machine learning library. For the purposes of these videos, I'm also assuming that you have at least some very basic understanding of the Python programming language, as we're going to be using it to develop our model. However, if you have zero programming experience, don't worry. The steps in this video will still be very easy for you to follow along with, and I'm sure you'll even pick up some knowledge of Python along the way. So, now that we're all set, let's get into creating our own neural network. Each time you construct a neural network, you should seek to follow the development process laid out here, which is going to include 5 critical steps. Those steps are input processing, building your model, compiling the model, training the model, and then evaluating the model. In the slides to follow, we will take a deeper look at these steps, how to complete them, and how they contribute to building your own neural network model. I will also be including little snippets of example code. However, this is mainly to provide you with general guidelines on different functions and steps needed in building your model. So make sure to adapt them and add alterations where needed so you can customize your own network. So the first step before even creating your model is making sure you implement some way to process your inputs. This can be done either inside or outside the model and assures that the data being fed into your neural network is formatted in a way that allows your network to effectively learn. Here are some of the key considerations to take into account when dealing with input data, starting with normalization. So generally, it is always good practice to normalize your data so their weights do not affect or make some values worth more than other categories. Now for images, this is usually pretty straightforward, as most images are going to have 3 color channels, RGB, red, green, and blue, which are going to have pixel values that range from 0 to 255. This data can be normalized either before inputting it into the model, or a normalization layer can be included in the model. It's important that if you normalize this data outside of the model, you must also remember to normalize any data that you're going to send to this model later. So usually I have found it just simpler to provide a normalization layer inside of the model as the first layer, which I have done inside the example code. Here, the first layer of the sequential model is going to be a Keras rescaling layer, which scales the pixels from their original 0 to 255 value to a value that's going to be between 0 and 1. I also want to mention that there is a Keras resizing layer, which allows you to resize your input images to a specified pixel size. The next important thing I would like to talk about is batches. For training purposes, TensorFlow expects and usually requires that the training data be in batches. A batch is the amount of samples the model will work through before updating its internal parameters, like weights and biases, through the gradient loss process, which I described in a previous video. In the sample code, at the top you can see a utils.image dataset from directory method, which is used to load images from a directory into a TensorFlow dataset. So here I've specified the batch size as 32. This means that during the training process, the model will process 32 samples before updating itself. So say, for example, the training data had 320 images. That means this model would update 10 times while making one complete pass through the data set, which is also known as an epoch. Now, if there is a batch size that does not divide evenly between a data set, then the final batch would just have less samples. The next thing I would like to talk about is the categories of data that are required for creating a model. These names are pretty straightforward, as training data is used to train the model. Validation data allows you to view things like the model's true loss or accuracy, as the model isn't trained on this data set. And then lastly, we're going to have the testing data, which is used as a final test to evaluate the model after training so you can see its accuracy. Most of the time, you may just have one big set of data, so it's really good practice to divide this data set into these three categories. The amount of test data you want is up to you, and you do have the option to just use your validation data for testing the model, as it's evaluated by the model in the same way. However, you never want to use training data for testing the model, as all models are prone to overfitting, which is a concept which we'll talk about later in the video. And this can cause the model to appear to be more accurate than it actually is. For the data used during the model training process, you usually want to seek to have about 80% of it used for training and then 20% used for either validation or testing. In the example code, this training data is loaded in with a validation split of 0.2, meaning 80% will be for training and the remaining 20% will be for validation. This same keras.utils.image dataset from directory must also be used in a similar fashion to load the validation data. The last important thing to mention when processing input data specifically is the flatten layer. Now this is going to be used mainly for images. Images are normally a 2D or 3-dimensional, referring to height, width, and their color channels. So this flatten layer basically unstacks the rows of pixels, lining them up and transforming the data into a 1-dimensional array. This is going to be seen in the model summary at the bottom, which basically allows you to see the shape and parameters of the model. I only included the first two layers here as they deal with input processing, and we can see in the example code as the first rescaling layer gives an output shape of the image, which is 28 by 28 pixels. These images are black and white, so it's only 2D as there's no color channels. But then after the flatten layer, the output shape now is 1-dimensional with 784 elements, which, if you know a little bit of quick math, is 28 times 28, showing that the rows of pixels have now been unstacked and lined up. Also, it's important to mention that this flatten layer should be included after all the convolutional, resizing, or normalization layers, and right before any hidden layers in the model. As we will see later, convolutional layers expect a regular image shape. So now that the input data has been processed, we can move on to building the actual machine learning model. So when it comes to building your model, there are a few different types you can go with. However, for simplicity, I will mainly be covering the sequential model, as they are fairly easy to understand and work well for many image, audio, structured data, and a variety of other applications. A sequential model is essentially a machine learning model that consists of multiple layers stacked on top of one another. Here, each layer is a plane layer, meaning it consists of only one input tensor and one output tensor. To define a sequential model, you simply need to use the tf.keras.sequential method as seen in the example code. From there, you can either add your layers as arguments, like I've done in the top code, or you can choose to define your model and then use the model.add method to add and stack layers on top of one another as seen in the example code on the bottom. Either is going to perform the same operation of building a sequential model. So as this model is made up of layers, there are tons of customizable layers you can choose from to design a model that fits your desired applications. Some of the more common layers are the input processing layers we talked about on the previous slide, convolutional and pooling layers, which I'll talk about in a following video, and lastly, one of the most important layers in your model, the dense layer. These are also known as fully connected layers, as the neurons in this layer are connected to every neuron of the preceding layer. So these dense layers are essentially what allow the model to define a relationship between the value of the input data and what the preferred output data should be. Basically the neurons in your neural network. You can set how many neurons you would like each dense layer to have. So in the example code, I have a dense layer with 64 neurons followed by a dense layer of 128 neurons. So these values aren't necessarily ideal. I just have them specified here for viewing. But overall, the correct size of each dense layer should be custom fit to your desired application. There'll be more to come on this in a video where I outline neural network model considerations like overfitting. You will also see a final dense layer included in my sequential model that has 10 neurons. Now this is the output layer, which is used to classify an image into one of 10 categories. Let's say we had a binary classifier, for example, duck recognition, where we're essentially just sending the network a picture and it's going to say if it has a duck in it or not. Then our output layer would consist of only one neuron, which depending on the activation and other function used would tell you either 0 or 1, which would correlate if the image has a duck in it or not. So talking about activation functions, you can see both fully connected layers contain the activation function ReLU, or rectified linear unit. This activation function is going to be seen in the graph on the top left and has become one of the most popular activation functions for fully connected layers. It's a simple piecewise linear function that's going to output the input directly if it's positive. Otherwise, if the output is negative, then it's just going to output 0. Activation functions essentially define the output of a neuron by deciding whether it should be activated or not, depending on its weighted sum and bias. The above example is pretty simple, but there are other common activation functions like the sigmoid function, which changes the input into an output value between 0 and 1, or the softmax activation function, which transforms the inputs into probabilities. Overall, the type of activation function you choose depends on your neural network and its activation. Because we're going to have like sigmoid functions, which are a very natural choice for binary classification. ReLU activation functions are going to learn the fastest. Meanwhile, softmax is best for multi-class classification. So again, you must carefully choose the correct activation function for each layer in your neural network depending on its application. So with a built model, our next step now is to complete the model and prepare it for training. Compiling your model is a necessary step that prepares it for training and involves choosing an optimizer, loss function, and any other metrics desired. This loss function, also known as the cost function, we went over in a previous video where explaining how a neural network learns. As we talked about, the goal of a neural network is going to be to minimize this function in order to guide the model in the right direction. So as a quick review, this loss function essentially is going to find the accuracy of the model by comparing how good or bad the model's guess is compared to the actual value. So here the example code is going to contain the sparse categorical cross-entropy loss function, which is an ideal loss function for an image multi-class image classifier. Again, if you're using a binary classifier, you would want to use the binary cross-entropy loss function. Here you're going to see I have the optional parameter logits equals true, which essentially informs the loss function that the output values generated by the model are not normalized. However, let's say that the softmax activation function was used on the output layer, then the outputs would be normalized in a probability distribution from 0 to 1, and then this logits would be set to false. So logits basically depends on whether your output layer is normalized or not. So now that we have this loss function, we know the network will update its weights and biases after each batch so that it may minimize this loss function. The optimizer now is the specified algorithm or mathematical method that helps us minimize this loss function. It basically guides us in tweaking the parameters like the weights of our network so that we can approach the local minimum. There are a few popular optimizers like stochastic gradient descent, RMS prop, momentum, and ADAM, which stands for adaptive moment estimation, which all work in slightly different ways. As used in the example code, ADAM is currently one of the best optimizers as it works with momentums of both the first and second order, which allow it to converge rapidly and also handle noise. This can be seen in the graph on the bottom left as the ADAM optimizer converges the quickest and it also reaches a much smaller loss as compared to the other optimizers. One parameter worth mentioning within the optimizers is the learning rate. This is going to specify how much the model weights can change in response to the estimated error during each update cycle. This parameter can be anywhere between 0, or essentially a very, very small number, and 0.1, but must be carefully chosen as a small learning rate can drastically increase training time, while too large of a learning rate can cause the model to converge too quickly upon a suboptimal solution and create an unstable training process. We'll cover more about learning rate, how it affects your model during training, and how to select the correct learning rate in a following video. Now, the last parameter I would like to mention when compiling the model is the metrics parameter. This parameter defines the metrics to be monitored while the model is training. This can help in calculating and estimating the performance of your model, which will come in handy once we begin talking about how you can evaluate your model, considering overfitting and underfitting. Now, the accuracy metric in the example code is pretty self-explanatory as it gives the fraction of images that are classified correctly. So now that our model is compiled, the next step is to actually train the model. Training a model is by far one of the simplest and most visually rewarding steps. To train the model, you will simply use the model.fit method, which fits the model to the training data. When using this method, you must pass it the training data and correct labels. In this example code here, we are passing it the training images and their associated training labels corresponding to which of the 10 categories each image is going to belong to. Note that if you are using validation data, as it's highly recommended you should, you must also pass model.fit your validation data. There are two different ways to provide validation data. The first would be as done in the example code here. The validation data was already separated as shown in our input processing section. However, say that you have not created any validation data and you only have the training data, you may include the optional parameter validation data equals the % of validation data desired to effectively split validation data from your training data set. This is seen in the comments in the example code. Another important parameter to specify is the epochs. Now, epochs is the number of times your model will pass through the entire training data set. We previously talked about how batch size affects the number of times the model is updated. We'll say there's 320 training images and the batch size is 32. We know that the model is going to update 10 times through each complete pass through the data set. So say we specify 10 epochs. This means that our model will update a total of 100 times. However, having more epochs doesn't necessarily lead to a better model. This is another parameter that must be reviewed and carefully selected such that you are neither overfitting nor underfitting your model. TensorFlow allows you to view the progress of your model throughout each training epoch. This is kind of the fun step where you get to sit back and actually let the machine do the work for you. The metrics displayed here are going to be the ones that are specified while compiling the model. And in this example, I have it displaying the loss and accuracy of the training data as well as the validation data. This is an important distinction between the training and validation accuracy that will come into play later when evaluating the model. Another important parameter you can specify when fitting your model is early stopping. Now, what this is going to do is automatically stop training your neural network once the performance stops improving. By definition, it's going to monitor the validation data so it can stop training based on your validation performance. The patience here is going to specify the number of epochs with no improvement before terminating training. So by default, it's going to be 0, and so it'll stop training at the first epoch that your model is no longer improving. This optional parameter is highly recommended as it can prove to be a huge time saver, as it can stop training once the model begins overfitting and can save you countless time waiting for a model to finish training itself while the training is no longer proving effective. So once your model has completed training, you can move on to evaluating its performance and even using it to generate new predictions. The evaluate method can be used as seen in the middle of this sample code here. The trained model is evaluated by using test data, say images for classification, to generate predictions, and then it compares those predictions to the actual label of the data. It's going to return the loss of the model and any other metrics specified, usually accuracy. Another important thing to note here is that to truly test the efficiency of the model, it is crucial that the data used for evaluating the model is not the same data that was used to train the model. So here you could use the validation data or test data. One good way to view the loss or accuracy of the model is through viewing its progress while training. Although not stated in the last slide when talking about training, the fit function that is used to train the model is actually going to return an object which keeps track of the model's accuracy, loss, and any other metrics that were specified when compiling the model. These metrics are tracked throughout each epoch during the training process, and it's generally good practice to view this on a data graph. Having either loss or accuracy plotted against the y-axis versus your epochs on the x-axis. Now this allows you to view the model's progress as it underwent training. Also, if you included validation data as part of your training practice, and based on what I've talked about here, I hope you did, then you should also include the validation loss or accuracy on the same plot. Having both training and validation data on the same graph allows you to look for signs of either overfitting or underfitting. Now just a hint, this plot here suggests a large amount of overfitting in the model, as the training accuracy is continually increasing while the test or validation accuracy remains stagnant. Another thing you can do with a trained model is use the predict method to do, exactly as the name states, make predictions. You can pass this method just one input, say one image, or you can pass it a whole data set of images if you would like. This prediction method will then make a prediction on what the image is and will return an array corresponding to the output of a neuron for each data point. So say your last layer has 10 neurons corresponding to the 10 different classifications your image could be. The predict method would then return an array of 10, giving the output for each tensor. For ease of interpreting, you can add a softmax layer onto your model, which will change the outputs to probabilities corresponding to the probability of an image belonging to each category. This is something done in the example code on the bottom right, where a softmax layer is added on top of the previously created model. From there, the model makes predictions on the test images, and we can review its first two predictions below. The first image probably is going to belong to category 10, while the second image most likely belongs to the third category. You can see for both of these predictions, the model is quite confident, and in fact is over 99% certain that these images belong to their associated categories. However, I do want to say that just because the model is extremely confident, that doesn't necessarily correlate to it being correct. So you should remain skeptical before fully trusting your model's confidence and should pay attention to the model's loss and accuracy while making predictions. The last thing I want to touch on is saving and reusing models, as it doesn't do much good to create a model that you will have to retrain every single time. So these basic functions will allow you to save and load your model so that you can resume previous training, load an already trained model, or even share your model with others. Now, loading a previously trained model or one trained by someone else can allow you to utilize transfer learning, which is another thing we'll talk about in a following video. So, by using the keras.callbacks.model checkpoint method, you can continually save the model's weights both during and at the end of training. This function could also be used to save the model every X amount of epochs, so then you can either load these weights depending on which amount of epochs prove to generate the most effective model. To load weights into a model, simply use the load weights function, but note that the new model must have an identical architecture to the initial model so that the weights can be shared between them. Saving and loading entire models also proves to be rather simple by using the save method to save the model, stating its directory location as an input argument. This model can then be loaded at a later time using the keras.models.loadModel method, and again passing the model the directory location as the input argument. So this was just a very quick run through of how to load and save your future models. Congratulations, you made it through another neural network video. Hopefully now you have a better idea on how to create your own neural network model and what things to consider during the development process. Of course, we covered a lot of material in this video, so definitely go back and review these concepts as necessary. You should also try and put your newly learned skills to the test. TensorFlow has a bunch of great tutorials which can help walk you through the same process and even provide you with functioning example code. Thank you so much for tuning in. In the next video, I'll go over some slightly more advanced techniques that will allow you to build a more accurate neural network model. So don't forget to like and subscribe, reach out over email if you want to chat, and never forget that with the right motivation and internet access, you can become an expert in any field you desire.